Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students, welcome again into this TV lesson learning program. My name is Jean-Marie, and today's lesson is for all of the senior 4 students. I think you are all feeling very good in front of your TV screen. So I welcome you to follow this lesson because it is a continuation of what we have discussed with the last time. So hope you remember the unit that we are discussing with is work, energy, and power. And the lesson of today is strain energy. And I want you by the end of this lesson that you are able to describe the strain energy, of course. So, and this is the reference. And more about this is strain energy. More questions, you are going to find them on page 251. And the other explanations, it is from this page 237 to 239. So let's have the quick review on what we have discussed with the last time. So the last time, we had a diagram. So the diagram that I have shown to you is a diagram that shows the stress, strain, and this diagram. What we have here, there are the points, and this point P, E, Y, U, T, S, and B, I tried to explain them to you, but giving you the titles into that lesson. But now, let's try to understand them, to describe them. Even if we try to describe this point, but let's now focus on this, but very quickly. So students, what we have as a description of this diagram, so P is the limit of proportionality. If the stress is relaxed, the wire returns to its starting length. If you remember, we had a spring by that time. The spring that we considered could now show that we have a mass, okay? So when putting the mass, and then when removing the mass, the spring could now return back at the point, so here. So when the mass is not on the spring, it is here, the spring goes back at the original shape. So here, what we are saying is if the stress is relaxed, the wire returns to its starting length. But up to E, we have it is the elastic limit, okay? So this, up to this point, the wire will return to the starting length of the, if the stress is relaxed, if there is no force or no weight on the object, on the material. And we are at this point, and now the two regions, here we have elastic region, plastic region. Remember what we have talked about the elastic deformation as this object that when the load is removed, this object will, when for elastic, this object will return back at the original shape. But when plastic, if the object, the load is released from that object, the object will no longer restore its original shape. This is what we have said the last time. Now, here from E, we start this plastic. We start where the object cannot return, cannot restore the original shape size. Do you understand, students? So it means that at Y is the yield point. This is what we call that, how we call the point here. The wire is permanently deformed, and at Y there is a sudden increase in strain here. So we say a sudden increase in strain, but a decrease of stress. Do you get that? So, and here we have the increase of stress, and then here strain also increases up to the point that we call the ultimate tensile stress. This is UTS. This is where the wire deforming is deforming plastically. Do you get the point? So remember, we are giving you the quick review on the diagram that we saw the last lesson. B is the breaking point. Now up to here, B breaks. The wire breaks. The material, the metal bar breaks. Do you understand that? So the wire breaks at a weak point. The value of the strain at the point is property of the individual sample of wire. So each material is having its breaking point. Not all of the materials have the same breaking point. Now, students, this is what we can now say about the diagram, and I want to use it even after into an example that we will be having. But before that, let's have the explanation on the strain energy. Now, students, what is the strain energy? What is strain energy? What can you say about strain energy? That is a question for you. Good. It means that strain energy is an energy that is stored into a material after the material is deformed. After you deform the material, the energy stored is what we call strain energy. In another word, when you remove something that is deforming the material, that energy can make the object to restore the size. But when it has passed this point Y and so on, then it cannot return back to the original shape, original size. Let's, what we are saying here, so this energy is usually, denoted as U, and by this time we can find this U if we consider a material, a metal bar. Remember, we consider a metal bar, and then a rod or a force that is exerting on it. That is the stress that we're seeing now. So when this metal bar here that you have, there is a force that is exerting on it, and as you see, the metal bar has a length L0. But when you exert this force, it is stretching or it is increasing the size because the force here, the force is exerted on this metal bar, and then there is an increase or a change of the size. Okay, there is a deformation. Here we have dl. In another word, up to this point, we can say that we have L, the final length. So this time you can find the L minus L0 equals to the change of length. But this time, what we want to find is the work done on the material. Material that we have is the, this material is the metal bar. So, and this time, this work is abbreviated, is stored into the material, into the object, material as a strain energy. So, students, that strain energy is what we have said to be this. Then this strain energy here will be equal to 1/2. Then we have force times the change of this. This is the elongation that we have, or the extension. So if you want, you can call it as the extension. Extension here. So this is the extension. So we can now make a change of this energy. And then remember, if it is stored, in another word, this is the strain energy. Then what we are going to find is the strain energy that is stored into this metal, into this bar, when the load is exerted, when the force here, F, is exerted on this metal bar. Do you understand, the students? So I want you to follow this. And if we have, let's have the very quick explanation from this. As you see, it is, this is what I was saying, I was telling you here. So after we have this CU, I think if you remember from this diagram, F there, F is going to be, from this diagram again, F will be equal to what? What do you think? This F is determined in terms of stress. Stress that we have explained the last time. Stress was shown to be sigma. This sigma equals to F over area. This is the sectional area of the material of this metal bar. Do you understand? So in another word, we have this F, which is equal to sigma, then times A. So this is what I've tried now to bring up here. So then after, we also have the strain that is there. It is epsilon. This strain is the change or the elongation of the original length of the metal bar. So, which means that as we have this, this is what we have here. And another thing that we have defined is this E. This E is what we have called elastic modulus. Elastic modulus is the ratio of this stress to the strain. And then we can find this sigma to be equal. No, we can find this E, which is equal to sigma over E. So you can now change in any way that you want. Do you remember that? So then, students, what is here is E. I've said that is equal to sigma over E. And this is true for the elastic material up to the limit of proportionality. You remember, this limit of proportionality is what we have said. It is true there only. When you pass by there, it cannot be respected. Then we can substitute what you have said as the force and what you have said as dl. Remember this dl from that expression of the strain. And then we can substitute everything there. So we find this strain energy equals to 1 over 2 sigma A times L0. Then students, this A times L0 is the volume of the metal bar. This volume, it means that the sectional area is what we have here. And this is A. And then we find the change in L times sectional area giving the volume of the metal bar. So now let's have the example on this, and here you can get to understand that, okay? So here we have the example. So let's have some examples. Then we solve this problem, okay? So have a look into those examples. I want you to have a look. Okay? So I think what we have as the first question, find the maximum load that can be supported by a steel cable 1.2 centimeters in diameter. UTS equals to 500 megapascal. So students, so let's have this equation number 1. For this equation number 1, what we are going to find is the F. I hope you see that. So this is determined when we know the value. The value of sigma is the stress. So since here we are given this UTS, or this what we have called the ultimate tensile stress, and then we have the value equals to 5 megapascal, and another is the area. The area is determined from the diameter that we have, and this is the pi r square. So, and the diameter, the diameter equals to 1.2 centimeter, and then what we have next is going to be equals to pi, then times 1.2 times 10 to the power minus 2 over 2. This is squared. So then we find F, which is going to be equal to, here we have the application of the formula. From the stress, here we have F over area, and this gives F equals to sigma times A. Then F can be determined from 4, this is 500 times 10 power to 6, and then here times Z. The area is that pi, then times 0.6 times 10 to the power to negative 2 squared. So the answer is going to be in Newton. So then students tell me, what is going to be the answer here, the force? The force will be equal to, did you finish to calculate? Students, did you finish to calculate? That's good. So the answer is equals to ndashaka calculator. Nagiye ntayijyanye kandi aya narebye karisiti kugira ngo mbwire. So anyway. Thank you. Then students, I think that we are finished now to make your own calculations. Let's make it now together. So that we substitute into the formula, and we find this 500 times 3.14, then times this is times 0.6 squared. This is equal to, the answer will be equal to, this is 5.7, then times Z, times 10 power 4 Newton. So we think that you have all obtained that answer. Then let's move to the second example. So this second one, it is a steel rod has a square cross section 10 millimeter times 10 millimeter and a length of 2 meters. Calculate the strain energy when a stress of 400 megapascal is produced by stretching it. And here we have the E. That E, remember what it is? It is the elastic modulus. Then let's make this calculation. So what do we find? We are going to find, then students, what are we going to find? We are going to find, let's substitute. We have to find, calculate the strain energy. We have said that is equal to U, and if you remember this U, this is for number 2, U equals to 1 over 2 sigma, you know what is that sigma. Then A times L0, this over E. And we have everything. We have this sigma. Let's substitute. We have 1 over 2 times sigma equals to that sigma. It is stress of 400 megapascal. That is 10 times 6, then times this is squared times the area that is 10 times 10, then times 10 to the power 2 minus 3. That is the squared. You see, as we multiply it, then we have to change it to meter. And what else? We have the length. The length equals to 2 meter. And the answer here will now be equal to into joule. So this is divided by E. The elastic modulus is 2 times 10 to the power to negative 9. That is the gigapascal. Okay? So then, students, we substitute again into the expression. And then what are we to find? This U will be equal to what? So can you substitute? So this is going to be, that is 0.5, then times Z, 4 times 10 to the power to 6, then this is squared, then times, that is 100 times 10 to the power to negative, that is power to negative 6, negative 3. That is, the all of that is also squared, and then multiplying it to 2, and then we divide it by 200, and this is 200 times 10 power to negative 9. And then we find the answer here is going out to be equal to, it is approximately equal to 80 joules. And let's have now this in number 3. Number 3 estimates the elastic potential energy. That E is the elastic potential energy stored in the wire before it breaks. Okay? So what is going out to be this? Before it breaks, in other words, what we are going to do is to use this diagram. This diagram that we have here is very similar to the diagram that we are having there. Okay? So because into this diagram, there is a force here, and there is an extension. So this is extension. So this extension was given 2 centimeters, and the force was given into kilonewton. So when you have the force, remember what we had into the stress-strain curve. Here we had the force of area, and here we had change of L over L0. That is the initial length. So if we have this also, we can determine the work done is always the area that is under the curve. In other words, if we were going out to determine the work, we would now say here we have A1 and this is A2. And then when we find the total, will now be the work done on this material to change or to deform that material. But now we have to find, what do we need now to find this elastic potential? Here, elastic potential energy equals to 1 over 2 times F times the extension. Let's say that is the DL. And then, so here we have, this is 1 over 2 times the force. You see, force before it breaks is already here. So this is 70 times 70 times 10 power to 3, then times extension, what we have there is up to 0.5. This is 0.5 times, this is 1/2 times 70, 10, 3 times 0.5 times 10 power 2 minus 2. And then this is into joule. So if we multiply this, what are we going now to find? We are going now to find the answer will now be simply equals to approximately equal to 260 joule. And this is in number 3. Now, students, let's conclude. I hope that you all remember what we have started asking ourselves, whether we will now be able to explain what is straining energy. Now you are able to explain what is stress energy and even to calculate. The application of this is into the analysis of the load that may now be exerted on the structure, on the materials, like into civil engineering, when you're constructing the houses, the bridges, you know, or you are sure the load that will be exerted on this bar, it is not going to destroy it, okay? So let's have now a homework. Homework that I'm giving you is the online homework. Students, take your pen, take your notebook, and then write down the link as it is given here. And then you place on it, and you will find 5 questions. These 5 questions, they are all related to what we have discussed here. And then click on submit, and I will know how many of you have followed. So here you have the link. Thank you very much for copying it, and thank you very much for following me today. And I wish to meet you again into the next time, having you did more other questions about this lesson. Thank you. Bye-bye.